Thank you, everybody, for joining my talk. We're going to be discussing how to simulate embedded systems with Zephyr. So here's a quick outline of the agenda for today. With all my talks, I start with the motivation, just to give some background on why we're doing what we're doing with my talk. We'll go over just traditional simulation in embedded systems, what personally I've used in the past. Then we're going to migrate to what sorts of frameworks does Zephyr enable when we're simulating embedded systems. There's going to be a few demos that are sprinkled throughout my talk, just screen recordings of things that I've been doing just to avoid any hiccups for a live demo, right, that we've encountered. And then just some next steps, right? What can we take away after this talk? Just a little bit about myself. I'm an embedded software consultant in the East Coast in New York City. I do a lot of design work, mainly focused on medical devices. I've worked on a LiDAR system, helped develop custom ASICs, writing embedded software for them, ag tech, a bunch of consumer electronics devices, so pretty much all over the place. My expertise obviously is in Zephyr, but also embedded Linux for a bit, as well as the Yocto project. I do hold trainings and workshops in my facility, so here, a few weeks ago, we had our first inaugural kind of in-person training. 5 people showed up. It was great. It was nice and tight. It was mainly focused on embedded Linux and Yocto. We're planning on holding another kind of in-person training throughout the early fall that's specifically geared to Zephyr. Facility's about a 10 to 15 minute bus ride from Midtown Manhattan. So, if you're interested, I encourage everybody to sign up for our newsletter to stay up to date on some future training events. So let's kind of talk about the motivation behind this talk. If you've been doing any sort of embedded development for a substantial amount of time, typical, and this is just personal experience, typical kind of legacy development workflow is embedded, again, the unfortunate thing is a lot of people think that it's software, it should be easy, so that's usually the last thing that's done whenever a project is worked on, right? You're usually waiting for the hardware to be ready where you can actually start the project in earnest. Sure, you can do so much, you can do a fair bit of work using development boards, but there are slight hiccups, slight gotchas, right? The pins don't match entirely. The SoC may not be the exact same part as it is on the development board. You write your firmware for the development board, you try to actually now run it on the target prototype, and nothing kind of works, right? So, you may have to kind of rejigger a lot of the assumptions that you've made. A lot of the development may have gone to waste. So really, again, in my experience, using the legacy development workflow, it not only just in real life kind of pushes out the work that you're doing, but it also encourages laziness, right? So, your estimates, you don't really think about the things that you're estimating for your management team about the embedded software because hey, hardware isn't even here yet. How am I supposed to estimate it out? Are the peripherals that I'm targeting going to actually work, right? A lot of, recent project that I worked on, the hardware guy, he picked a really obscure peripheral, right, to light up a 7-segment LED. I had no way to test it out because it was there was no development board that targeted it. So well, how do I estimate this out when I don't even have the hardware in front of me? And what happens is, well, you can't estimate out what your tasks are really gonna, take, right? And so what ends up happening is, okay, the last sprint of the project timeline is once you receive the hardware, well, now you have 2 weeks to get the project done, writing the firmware, getting it tested, making sure everything works. And what usually happens is timelines get pushed, people get upset. So, that's the typical kind of development workflow. And like I said, this, for me anyways, it encourages laziness, right? So again, sure, I can put together numbers, I can put together timelines, I can put together estimates, but in the back of my mind, if I'm just waiting for hardware to be ready, well, how can I really put some real thought into these estimates, right? So, it's just, you really start thinking about the project when, you have the green light that, hey, hardware's ready, it's gonna be shipped. Now you start thinking about the estimates. Now you start thinking about the design and architecture. Again, that's just personal experience, right? May not be the case for everybody, but for me, right, this being in this mindset of, hey, I'm really going to start thinking about firmware when hardware is ready is really a poor mindset because it just encourages just laziness, right? And it just results in delays. So there have been like a fair bit of developments recently, right, in the embedded software landscape, right? And so, you know, we should be encouraged, or we should be encouraging others to adopt a more modern development workflow, right? We should immediately start thinking about designing our embedded software, right? Assuming that the hardware is not ready, assuming that, hey, like how much can we abstract out the hardware as much as possible so that we can focus right immediately on designing the architecture, design and architecture, and ideally implementation of the embedded software that's not necessarily tied to the underlying hardware, right? So the mindset that we should be going into when writing kind of modern embedded software following this modern development workflow is that, hey, the actual number of lines of code that we personally have to write, right? I'm not talking about the entire framework, the entire OS that we're dealing with. The things that we're directly responsible for, less than 20%, you know, just again, my personal figures of merit, less than 20% of our embedded software should be dependent on the hardware, right? At least 80% should be just hardware agnostic. Hey, I'm going to design and architect my firmware so that, you know, it's not dependent on the actual underlying hardware or the design decisions that are being made by the hardware engineers, right? So that sets me up, that mindset basically sets me up for success. If I'm in that mindset, then, you know, I don't personally promote my own self to be lazy. Right, so the question is then, well, okay, we have this great modern development workflow. All right, well, how do we, like, what are the details, right? Sure, we can, you know, speculate, think about, you know, we're not philosophers, we're engineers, right? So we need actual tools, we need actual frameworks to help us be successful in writing our embedded software. So one of the first things is, well, testing, right? How can we, you know, if we're going to break up our embedded software so that it's as agnostic as possible from the underlying hardware, how can we test our embedded software so that it is independent of the hardware, right? Is there a pattern that we can use for this testing, or do we have to research different frameworks? Do we have to come up with our own sort of pattern and spend more time doing that, right? Simulation, right, or emulation. Can we, you know, simulate or emulate hardware that's, you know, part of the SoC that we're using, that's inside the, that is the MCU? Can we simulate or emulate hardware that's outside, right? Can we, let's say we have a multi-node system. Are there tools out there, are there frameworks that we can leverage to be able to test out like a multi-node system so that, again, right, the last thing you want to do is, hey, we have, you know, forget a 100-node system, we have a 10-node system, right, even. You know, we have the hardware ready, like how do we launch these 10 nodes in a bunch of different configurations and see how our embedded software is going to work? That's a really poor way of going about testing your embedded software because obviously you're limited in time and you don't have the appropriate resources or time capabilities to be able to exercise as much of the different scenarios that your product is going to be launched in, right? So are there tools that we can leverage to be able to start this testing, start the simulation as soon as possible? So again, right, if we have an ecosystem that can help us with this testing, with this simulation, then that would be great. And that if it leverages best practices and mature frameworks, that's even better, right? Because the last person that I trust to come up with like a robust framework, right, a robust kind of simulation environment is myself, right? I don't want to be doing these things, right, because I know, like, A, that's not my job. I'm taking time away from my real job, and I'm gonna like not do it the right way, right? So are there people that are smarter than I am that have kind of come up with these sorts of frameworks for best practices? And the answer is yes, right? So Zephyr is something that we're gonna see how in the next few slides later on, how it kind of encourages some of these modern best practices. That's not to say that, you know, embedded simulation hasn't been present in embedded software and embedded systems. It obviously has, right? So QEMU, right, is one of the, you know, more well-known platforms that are and frameworks that have been used for embedded systems. It's predominantly known for Linux. Like, hey, you want to, you know, try out something in the Linux kernel that, you know, could be targeting your own architecture or another architecture. most of the time you just use QEMU for it, right? It's developed by Fabrice Billard. If you don't know him, I encourage everybody to look him up. He's like he's done some really great, some great work and continues to do so in like a whole slew of like, he's not just embedded software. He's done like things in JavaScript. He's like written his own algorithm to like calculate pi really efficiently. So it's like, has a really cool backstory, a bunch of different projects he's worked on. So like I said, right, QEMU has been mainly used primarily for embedded Linux systems, right? It has cross-architecture support. You can essentially emulate ARM or RISC-V system on x86 or 64 on a Intel or AMD-based system. And it's really valuable if you to be able to use before your complete hardware is available to you. So typically, like if you're doing anything that's related to building Linux distributions, you don't necessarily have the hardware that's available to you. QEMU is like a really great framework that you can use to not only emulate your own system, but then you can actually write software to emulate an external driver, an external device, and then see, hey, if I can target this external device based on the data sheet that I have in front of me, I can write a driver targeting this device, and then once the hardware is available to you, well, you've done a fair bit of the work, and maybe there's some small nuances that you need to account for. Data sheets aren't entirely always accurate, right, until you get the hardware, but then most of the work that you've done has already been done. So not only, the cool thing is that QEMU has also been used to test and to simulate like non-Linux based systems. So, there's support out there for bare metal, RTOS based applications that we can use to in QEMU to be able to target. So, modern IDs have incorporated QEMU into their workflow so that, you have basically like a picture of the board, you can press a button and it actually emulates a button press in your underlying simulation. And then you can see LEDs light up based on how your firmware is responding. And this is really great, right? This is really a great way to make sure that, hey, if I'm loading my embedded software on a particular target board, then this is a great way to validate at least, some of the functionality before I actually get the hardware. So QEMU has been around for a fair bit, right? It's nothing new. But there are more frameworks that Zephyr has introduced that we can kind of build off of and expand our kind of toolbox, right, of tools that we can use as embedded software engineers that are developing products. So just real quickly, Zephyr is not just an RTOS, right? It's one of the cool things about Zephyr is that it's an entire ecosystem. There's maintainers that are kind of responsible for the different subsystems. There are people reviewing code, right? It's not just here, here's some piece of code that you found on the internet, right? You don't know the quality of it. There's a whole community behind Zephyr, and then when you kind of leverage Zephyr as part of your code base, there's some guarantee of quality that you can be rest assured of. So along those lines, right, of it being an entire ecosystem, it has just inherent support for different types of simulation and emulation environments. One of the big things that I like to use in all my projects is, its support for hardware agnostic kind of testing, right? So, you can simulate what that encourages, right, through Z-test and Twister, is that you can decouple your business logic from, let's say, the application logic that sits on top of the actual drivers themselves. So it encourages you to design your hardware, design your software so that, hey, this is my business logic of here's strictly just C code, whether it's a state machine, whether it's other logic that I have. And Z-test and Twister basically encourage you to write your application so that you can start unit testing your different modules just independent of hardware, right? It just runs as a binary executable on your x86 machine. You go through tests to make sure that, hey, in different scenarios, in different environments, that your state machine is actually functioning properly, right? And so a lot of times we get bogged down that, hey, we're just writing unit tests to do code coverage analysis. That's not how I really think about it. I want to make sure that the state machine and logic that I'm implementing is actually working as I'd intended to. So I come up with, meaningful just cases, right, that I want to test against. And then I also come up with corner cases to make sure that, hey, my software can account for the different scenarios that it's going to face properly. Another useful tool is BabbleSim, and it's meant for like physical layer, like RF emulation for, let's say you have multiple nodes. They have support for BLE, 802.15.4. You can also expand it. I've worked on this recently where you can expand BabbleSim to kind of account for your own, let's say, specific protocol at different frequencies. It's really, BabbleSim is really a niche case of why you would want to use it, but it's another tool, again, that's kind of backed and supported by Zephyr that you should leverage whenever you're developing a particular application. The other kind of tool and framework that we can leverage is Renode. It's really valuable when you want to, be able to. We're going to see, like, I equate it to a modern version of QEMU, right? It can emulate everything from down to the SoC all the way up to multi-device systems, right? And then you can. It offers a fair bit of flexibility and a lot of capability that we can use across different devices in one device and multiple devices to be able to kind of make sure that our system is appropriately implemented. So we'll quickly go over kind of some details about some of these frameworks. So Z-Test, right? This is a great HTML web page on Zephyr's documentation on the details of Z-Test. And it's similar to other testing frameworks. It provides basic assertion macros and a generic test structure. You define a series of tests by calling like the Z-Test suite macro, and each test is defined by Z-Test macro. And again, going back to what this encourages, your final test application is a separate application from the binary that you're going to be loading onto your hardware. So what that encourages is a design that, hey, you're going to implement the different modules, right? The different code bases, right? The source files as a library, right? So everything is now a library that's going to be incorporated into your final application that's going to run on the hardware, but also you're going to be selecting which source files are going to be part of your test application. So now it encourages basically you to decouple your business logic from the underlying hardware. So if your test application, if you just want to test your business logic, well, you can just incorporate those source files from your library in your test application. But then in your final application, well, you're going to include everything, including the actual modules and source files that interact with the underlying hardware. So just having this capability to be able to write unit tests, write test applications is a great way to kind of forces you to kind of think about writing code in a modular fashion so that, hey, the business logic side of this, I'm going to write it such that I can successfully unit test it with just this test application, but then now I can also bring it in to my final application that interacts with the hardware. So it's just a great, so that you're not just like kind of combining code that's interacting with the hardware with code that's exercising business logic. You have a real reason to kind of decouple the business logic from your underlying hardware. There's two kind of main ways to kind of to use Z-Test. One is unit testing. It doesn't compile the entire kind of Zephyr kernel. You basically just add module source files to unit test kind of the binary that's provided by Zephyr. You already have kind of a precompiled binary that's when you want to unit test something and you want to be able to incorporate, let's say, multiple threads into your business logic, and you want to make sure that you want to be able to test that. Those are there's POSIX compliant kind of APIs and implementations that are provided by Zephyr to be able to kind of test these underlying things. Then there's integration testing, right? Now that compiles the entire Zephyr kernel and the test application, and that's useful if, let's say, like your business logic also incorporates different constructs within Zephyr, and you want to make sure that, hey, my timing is correct from strictly like a functional point of view, that it's not bogged down by the nuances of the hardware, but that you can incorporate the actual underlying structures in the kernel to be able to accommodate, to be able to test your actual implementation. Twister kind of goes hand in hand with Z-Test. It's the actual application that runs these tests. And it's basically a framework in addition to an application that can build an application for your specified board, run them and checks the results against assertions in the z-test that you specified. It supports both execution on the host PC using the native sim target, and we're going to see native sim kind of come again when we talk about Renode. And it also, the cool thing is, right, it also supports execution on the target board, so that let's say you run your business, you write your test application on your native PC, you run your test, everything works fine. Now that you have the hardware, the first thing you should do is actually run those tests again on the target hardware to make sure that, hey, are there any nuances of the hardware that are affecting potentially your timing that are causing your test to fail? Because, before you actually test your final application, at least at a minimum, just make sure that your tests are passing, right? So you can do both with z-test and Twister. So like I said, right, the important thing to keep in mind and, to come in with this mindset is your final application is not the same as your test application. And I like this. I like the fact, and I don't think that this is emphasized enough, that the fact that you have this encourages you to create this mindset that, hey, how can I decouple, or how can I write my software so that as much as I can leverage in my test application that I can leverage in my final application, because as much as I can test meaningfully test, the better the quality of my final application is going to be, right? So, just going to any project with this mindset, it forces me to write design documents as soon as possible, right? So if I go into this mindset that, hey, I don't need to wait for hardware to be ready to start writing embedded software and to start writing my business logic, I can immediately start writing design documents, immediately start coding up state machines, right? Decouple the business logic from my underlying hardware, right? So again, by creating this library, not only that, but then now if I just have strictly C code, that library can potentially be used in other places as well. And like I said, the important thing that this emphasizes is writing, and running just meaningful tests, right? To ensure that your application matches state machine design, right? A lot of the times we get bogged down by writing unit tests because we need to satisfy just some, code coverage metric, right? I don't like to think about it that way. I want to write tests to make sure that, hey, am I covering edge cases and corner cases appropriately, so that, I can implement and correct my software, my implementation for some weird corner case that maybe, it'll get hit 1% of the time, but I still want to think about it and make sure that my application is robust enough against it. So here is just like an example of how you would go about writing a z-test. Again, you just have that macro that defines, you basically, what you do is you define, state variables as externs in your actual application, and those are defined in the library itself, right? So those are external to your test application. And then what you would normally do is like, okay, I'm going to, emulate a particular scenario by setting up a state variable, by setting up a counter, right? And I'm going to call a function into my library and see, okay, did the variable get updated to what I'd expect it to do based on, what my test is saying. And so on the top, you have like a pass case, right? And then on the bottom, right, it's really, again, just testing and exercising the state machine that I've implemented for a particular project that I was working on. And then at the bottom over here, you just are basically listing that this particular source file consists of a bunch of different tests that are meaningful for my kind of application. And again, the key here is if, let's say, you have external state variables that are defined, right? I want to make sure that my state transitions are correct in the actual implementation, and they match my design. So essentially, like, the design documents are dictating my test cases, and then I'm using the test cases to verify my final implementation to make sure that the implementation is correct. So what's the difference between kind of z-test and Twister against QEMU, right? So QEMU, if you're not familiar, you can run like an entire system with a separate kernel. You can leverage your own kernel, right? But it's really heavyweight, right? It's really meant to be able to run an entire system and emulate like potentially a different instruction set entirely. With z-test and Twister, that's not the case, right? You're using the native sim board, and it's not emulating anything. It's actually just running the instructions of your native PC. So you're actually running something that's compiled for x86 or x64. And like I said, if you have certain kernel behavior that's implemented as part of your test application, you're using those POSIX APIs, or those POSIX implementations of different thread, let's say different tasking, different threading, that is part of the POSIX API, and you're just implementing that, and those are implemented just using standard x86, right? And it's much lighter weight, right? So just kind of a comparison between ztest, Twister, and QEMU. So now let's move to BabbleSim, right? So BabbleSim is a physical layer kind of network simulator. And it's, again, like I said, it's a really niche case on why you would want to use BabbleSim. It's really meant to kind of help in developing network protocols and devices. So you can test multiple nodes in your network, and they can be heterogeneous, and you want to be able to kind of validate like different topologies and different kind of weird scenarios over a single PHY. And you want to make sure that, okay, in different scenarios, how well does your software accommodate for different topologies, et cetera. The drivers are written there are certain drivers that are written as part of BabbleSim that simulate and emulate kind of the underlying radio devices. And the applications that you build for BabbleSim, right, they're compiled and they're run as part of a single kind of simulation. So basically, if one device kind of blocks, right, in your entire simulation, then your entire kind of simulation pauses, right? So for example, if you want to debug something, right, and let's say you hit a breakpoint, your entire time basically stops in your entire simulation, and you can kind of analyze the properties of different nodes. So this is kind of just a diagram that demonstrates like how that sort of works. So you essentially kind of simulate multiple devices in software, and they share essentially the same PHY. And then there's a single kind of BabbleSim application that's running in the background that's kind of coordinating all the different transmissions and receptions across the different devices. And so, yeah, so this is kind of another description on like how the actual software kind of comes together. So you have your application, your Zephyr kind of kernel, the stack, the drivers, et cetera, all written up. And you're going to actually compile it for a variant of the native SIM target called the NRF52 BSIM. So that's a specific target that, again, it's still executing x86 instructions, but it has abstractions implemented for that are specific to the NRF52. And then you run that on the native SIM target. But then BabbleSim also has these models that are implemented for the underlying NRF52 radio, and then you basically combine those two together and you run them in a single kind of BabbleSim simulation. So here's like a quick kind of demo of it. So here I'm just going to compile, like a BabbleSim variant of like, say, Hello World. And again, right, so the key thing to remember is that you can run these implementations independent of BabbleSim, right? So if you have support for some sort of network operation, right? So here what we're seeing is we're just getting the printout for one device. So we're going to see this in a more kind of sophisticated implementation later on. Like you'll see like how we can see like the different nodes in our simulation kind of interact with one another. Here it's just like, okay, one node, nothing really too exciting. We're just kind of demonstrating like what that looks like in a BabbleSim environment. This is, yeah, so now this is basically kind of showing two devices in BabbleSim. So here I'm going to basically just use the central and peripheral kind of BLE samples for the heart rate monitor in Zephyr. And so I compile it for one. I copy it over to and I have BabbleSim kind of pre-compiled. So I pre-compiled BabbleSim. I built it for, what is that? I think that's the central. I copy over the central binary to one particular location. And then again, I just now build the peripheral heart rate monitor sample and copy that over to into the same kind of location, but just call it a different binary. And here, I'm basically just going to run the simulation now. So here, I essentially have, see that? Right, and so this is kind of just saying that, hey, I'm going to run the central and the peripheral both targeting, like you specify which simulation environment with the -sim option, and then within the simulation itself, you tell it how many devices it should expect. So if it only, let's say in this case, we're specifying 2 devices in our simulation and only one is connected, it's going to wait until the other device connects, and then it's going to launch the entire simulation. And you can also specify like how long you want the simulation to run. Right, and so that last part is basically just highlighting like how long we want the simulation to run. And here, like this is where, you know, things are more exciting that are happening. And between the green and the red, it basically shows which device the printout is coming from. And then we can kind of see like, okay, as the devices are communicating with one another over BLE, in this case, like what the interaction looks like. Okay, so the question is, right, why, right? Who cares about BabbleSim? Like, and the answer is, well, not many people are gonna care too much about BabbleSim, right? BLE is, you know, well established. And you know, if you really look at the repository source code for BabbleSim, in earnest, it only really targets the NRF, you know, 5X, the Nordic kind of hardware models, right? Well, you know, it's not just BLE, right? It also targets 802.15.4, and that opens up a whole slew of opportunities, right? So for example, let's say, and I've worked on this sort of project in the past, you have, let's say, you know, a particular BLE mesh project requirement, and you have, let's say, hundreds of devices. How do we account, right? How do you prove to your client, to your customer, or to your boss that, hey, this routing protocol that I've implemented using BLE mesh, you know, works to meet the requirements that you set forth to me? How do you prove that without any hardware? Well, you can use BabbleSim to kind of create these topologies, you know, create these different network environments, and then, you know, make sure that your implementation of this, you know, routing protocol is working as you expect it to work, right? Without waiting for the hardware to be available and coming up with these crazy scenarios in real life to be able to account for this. I mean, that's definitely a useful thing to have, but you don't want to wait to that last point to, you know, find out that something fundamental is just wrong in your design. So, you know, this is where kind of BabbleSim kind of really comes in handy, and you can specify, right? So you can specify different channel models. My background is wireless, so like this stuff really excites me. And so like, you know, you can specify the different attenuations, different kind of actual topologies about, okay, you know, this link has this much attenuation, the link between these 2 nodes, et cetera, et cetera. And so, you know, you can really get really crazy with, you know, how you're specifying these topologies, and then you can run your BabbleSim environment. And again, this kind of goes hand in hand with your testing. You know, you can combine your Z-test to make sure, okay, you know, if I combine this with my BabbleSim and I want to be able to like, you know, ping from this node on, you know, this in this enclave to like this other node on the other side, you know, what does that ping latency look like, right? And I can trace that by combining both, you know, Z-test and Twister with my BabbleSim simulation, right? And so that gives me a really good idea of under different scenarios, different RF conditions, like how well is my system going to work without having to wait for, you know, final hardware to be ready. So the last thing we're going to talk about is Renode. And so this is a development framework, and it can kind of emulate the entire hardware stack. And it can also kind of emulate like multi-device applications. I really like kind of after reviewing and working with Renode last couple of weeks and months is like I kind of equate it to like a modern version of QEMU. It's like QEMU, but it's for like IoT devices. You can define your entire hardware stack. You can define multiple devices across the network. And one of the cool things is it's not really restricted to Zephyr. You can kind of, as long as you have like an ELF binary or any sort of binary, you can just load it onto your system in Zephyr, in Renode, and you're kind of good to go. The only thing that's really kind of missing in Renode is like the support for external devices that you would normally have for QEMU. And we'll see kind of how that's mitigated in next couple of slides. So here's kind of like, you know, the main thing, one of the main things in Renode is this functionality called the monitor. This is how you as a user kind of interact with Renode. You can basically like set up different devices and start your emulation, stop your emulation. The monitor is what you really use to kind of interact with Renode. And there's these scripts, right? Renode scripts with a .resc extension. And it basically kind of takes care of you, like it would, like if you're familiar with like Bash or Linux, you know, scripts, it's kind of something similar, where it kind of takes away the monotony of like doing the same thing over and over again. If let's say you have a particular platform that you want to target, and you're always doing the same thing with that particular platform, or you have a particular device, right? You can just encapsulate that into a Renode script, and you know, you can just kind of load that script and it'll take care of kind of handling that for you. So here we can see on the left, this is directly from Renode's codebase, right? All this is doing is just running a Zephyr shell demo on the NRF 5244840. And all it's doing, it's really just loading this REPL file, and that's just a platform. And like I said, right, we're loading in any ELF. Like here, they're just fetching a precompiled Zephyr shell ELF file. We can load any ELF that we want, right? We can load any binary. And that's one of the cool things that I like about Renode, that it doesn't necessarily have to be Zephyr. You can you know, try any other binary that you want. You want to be able to emulate different devices or different firmware. You know, it's a great tool to use. Platform, so if we see here, right here, we're loading up a particular platform. It's defined by this REPL extension. You know, if you're familiar with, you know, obviously Zephyr and Linux, right? It kind of reminds me of like a device tree. So here we can see this is the platform definition for, let's say, a 52840 development kit. It's including the actual 52840 CPU. So it's kind of like a device tree in that sense. And then here, you know, it's overriding some of the existing, you know, it's defining specifically like, hey, you know, this GPIO corresponds to this device, right? And et cetera, et cetera. And then if we drill into the actual CPU REPL platform, right, it's specifying the exact specifics of that particular SoC. So in my mind, like you know, it's kind of borrowing a lot from device trees, and just in that kind of framework, which I think is great, right? It's just reuse, a lot of reuse, et cetera. One of the key points of Renode is the system bus, right? It's kind of a construct in Renode itself, which serves as a mechanism for kind of peripherals or devices to communicate with one another. It's kind of this abstraction that they're leveraging to be able to emulate kind of device interaction. So the other kind of cool thing about Renode is that it has like just native GDB support. So let's say you create these machines in Renode, you can kind of in Renode debug them. So you have, let's say a fake machine, right? You have a fake debugger that's attached to it, and now you're kind of like, in your little, I don't know if you guys are old enough to remember like Second Life or something, but like, now you're in your, own little fantasy land without any hardware, trying to like, debug firmware that you're writing on, fantasy kind of hardware, which is great. And so let's say you hit a breakpoint, right? The cool thing is, in real life, right, if you're gonna hit a breakpoint like in the middle of a SPI transaction, right, the device is not gonna pause, right? It's just gonna like time out because like, hey, what happened all of a sudden, or I2C, right? The cool thing about Renode is that, well, time just pauses, right? So you can kind of methodically like understand kind of what's going on, how the device is behaving on the other side whenever you're kind of doing some sort of interaction. And also it's great if you have like multiple devices that are talking to one another. In real life, it can be difficult, like just running, how many like JLinks can you afford to be able to like, debug like 3 different devices at the same time, right? It becomes pretty hairy pretty quickly. So with this, you can actually like debug the interactions, and again, test out your different test cases to make sure that that your implementation is working as expected. So like I said, one of the things that I hope to see in Renode in the future is like support for external devices like QEMU has, so that right now, you basically have to fake data and pass it to Renode. Like, if you have temperature data, you can issue a command to kind of like specify temperature or humidity, and even that's pretty limited. Or you can specify like a binary file. They call it resd, like a particular binary format that you can have like a stream of data that can be fed into your simulation to be able to see how your device reacts to it. So, it'd be great to kind of like along the lines of like what QEMU is doing, be able to kind of emulate devices as well that are directly connected to your device itself, have different sensors, et cetera, and be able to like see real time, like, hey, is the device, is my implementation working as it should? So to summarize, right, these are kind of like tools in your toolbox, right? Don't be overwhelmed by these kind of frameworks, right? You just have to know when to use them, right? Like, all the tools, certain tools are good for certain things. And so, just being aware of them, just kind of like knowing that they're there and what they're good for is still useful to be able to say, hey, I'm developing this sort of, project, right? I'm developing, like a custom network protocol, right? For this particular, really obscure waveform or whatever, right? Okay, maybe, BabbleSim is a good thing for me to, start thinking about early on so that I can make sure that at least the hardware agnostic network protocol side of things is implemented as correctly. And then when hardware comes into play, like, okay, I can worry about that later, right? So just to kind of, again, summarize, right? Like some of the lessons learned that I'm trying to apply into projects moving forward is always use Z-test and Twister, right? And one of the things that you can do that is immediately set up your CI/CD like from the beginning, because that forces you to set up your testing frameworks immediately so that as soon as you have your first push, right, up into your repository, your testing framework is running immediately. You're not waiting for, halfway through your project is done to start thinking about it, right? So always use Z-test and Twister, write meaningful unit tests. If you're familiar with GitHub Actions, I try to have like like my own hosted runner so that I have like another board that's connected. I can run these tests not only in the cloud, but also on the actual target board itself to make sure that, hey, I'm not just overlooking that the tests are indeed passing, right? You should, leverage BabbleSim if, let's say, you need to test like tens of nodes. If you're coming up with like a custom protocol, right, you want to make sure that your protocol meets the requirements, that the implementation meets the requirements that are set forth. BabbleSim is a great tool to kind of like make sure that you're emulating the underlying PHY as accurately as possible. It's really meant for like a scientific tool. It's really accurate. I think the phrasing is you run BabbleSim like hundreds of times on the same model, on the same channel, right? It's going to give you the same result like those 100 times, right? But again, it's really niche. It's only for specific instances of when you would use it, BabbleSim. I'm starting to use Renode basically all the time now, again, because I don't want to wait for hardware, and I have a tool that can emulate hardware for me. I can build up my own platform now, right? It has support for a bunch of different SoCs. I can take basically, let's say the nRF52840, if it's a Nordic chip, if it's an nRF52-based product, I can take the development kit, just copy it, make tweaks to it to adjust kind of like the pins, et cetera, based on the schematic that I get. And I can get started writing firmware to target even a custom board, even without hardware being available. So what are some next steps, right? So, I'm going to put my money where my mouth is. And so the plan is to kind of demonstrate like in, next talk, next blog posts, et cetera, kind of demonstrating this cohesive workflow using some of these frameworks that we have, right? Okay, you have, let's say, a project requirement. How do you go about writing your testing frameworks to make sure that it's, covering as much as possible, right? As many meaningful test cases, right? Is BabbleSim, how do you determine what is the gate, what is the question that you ask to determine is BabbleSim a useful tool for you to test? How do you go about like, okay, you have a custom board, how do you use Renode to like, okay, now the hardware guy gave you the schematic, right? Initial schematic. All right, let me now create my own custom board in Renode. Let me start testing my embedded software as quickly as possible. And okay, when the hardware comes in after iterations of the schematic and layout, all right, now I can start testing in earnest, right? But getting the idea is that we want to be able to start doing as much as possible, as quickly as possible, start writing as much code and testing it as possible until we get the hardware. So that's all I have. There's no question slide, so anybody has any questions or comments, or they want to throw something at me, welcome to. Yeah.
You mentioned the Renode format looking a lot like device tree. Are there any tools that automate converting from like an existing board device tree to the Renode format so you're not handwriting and making sure they're the same?
Yeah, so the question is, I mentioned that the Renode kind of platform structure follows like the device tree or it reminds me of the device tree, right? So the question is there a tool that exists that can convert like a device tree to a Renode format? I don't know of any tool, but yeah, I think that would be a great kind of thing to add to Renode to be able to support that layer, where you could just, with a tool, right, just convert the already existing device tree into a platform. Yeah, I think that's a great idea. Yep. Oh, yeah, so I'm working on an embedded Linux book, I guess. I have one of my reviewers here. So, yeah. I guess behind.
So, with the Renode, you mentioned that it can sort of give some sensor data from a binary file or something. But I want to test real-world user interaction or something and simulate that, like the button press, or maybe like a accelerometer. I want to be able to simulate some gesture interrupt point like accelerometer. Is there a way to mock out those tests in Renode and make sure that my software is responding to them correctly?
Yeah, I don't know to that level if they have that. Like, I think with the IMU for sure, like that's what the intent was for this binary kind of format. Like, you can specify different channels, you can specify different sensor type. It's like that's encoded in that binary format. But yeah, like I don't think they have anything like, you would see in like QEMU, like, hey, like in the GUI, like a button press and like, oh, stuff happens. So yeah, I think I'd love to see that in kind of the near future. I think it would be really powerful.
Zephyr does have like a mock GPIO driver, so you can actually trigger a GPIO things to simulate it that way. Yeah, sure.
Then for the mock, like how would you trigger the mock GPIO though?
Currently, when you set it up, you give it a sequence of events with like timing between them, and you can basically have it trigger like GPIO interrupts, new GPIO states, etc., so that you can drive it that way.
Oh, interesting. Yep.
What's your experience with performance of Renode? I know when I was looking at it, it seemed like it was pretty slow, but I wasn't sure.
Yeah, I think recently like it's gotten much better. Where like it's I agree, like it was pretty slow kind of early on, but I think the performance has improved like a fair bit. Another question. Oh, sorry, I didn't see your hand.
For BabbleSim, like how involved is that like channel modeling? Is it like just purely statistical, or can you like is it good like IQ level and I could like throw gene gradient in the middle and stuff?
No, it doesn't operate on IQ samples. Like you need to, like it needs to be like a higher level kind of model that it uses. Yeah, they don't operate on IQ samples. I think it operates strictly on like packetized data. Yep. Cool. Thank you.